Okay, it's great to be here, and we're neighbors, so it's fantastic to come today and meet so many friends and scientists that work in similar fields. So today I want to show you a little bit of our recent work in the area of metamaterials and plasmonics. For who is not familiar with the field, this is just a slide to summarize what it is. These are some of the structures that we have built along the years in my group, but there are many groups that work in this area. The idea is to realize emerging properties from artificial materials by controlling arrays of nanoparticles in specific ways, such that we can control not only just the materials involved, but also the arrangement, orientation, alignment, density of these materials. So the goal is to get electromagnetic properties that go beyond just mixing two materials. Here, for instance, you see gold and glass, but the properties of the bulk material are very different than just a mixing of the two. They are emerging from the degrees of freedom involved in this design. The area has become extremely popular, especially in the last few years, when a few groups have suggested that we can combine these properties with plasmonics, with strong resonant excitations of nanostructures that allow you to actually control at the nanoscale, at deeply subwavelength scales, the response to light. And therefore you can mold actually the optical wavefront, change the pattern of an optical wavefront at will, imprint on light over a thin surface this orbital angular momentum or steering beams and so on. And this happens over deeply subwavelength scales, both in thickness but also in the resolution over which you can achieve these effects. Some of the holy grails of this field of metamaterials, you may have heard about this, the idea that if you can control the direction of refraction of light and bend light with a negative angle, you can actually realize planar lenses that overcome the diffraction limit and have a focus that does not is not just a point, it's actually half space. Also, you can build these invisibility clocks. If you can, again, redirect an impinging light beam in a way that it avoids a certain region of space, then this region of space is effectively hidden, or it's cloaked from the excitation. These have been very exciting ideas, but we have not seen really the fruits of these ideas in terms of practical devices that actually work and that go beyond what technology already offers us. The main reason for that is that these metamaterials and metasurfaces have been typically are passive and therefore tend to be heavily affected by losses. The reason is that we enhance these light-matter interactions in subwavelength scales, and with the enhanced interaction comes also enhanced loss and absorption. Also, they are typically time invariant, so it's difficult to reconfigure these materials after they are built for a certain functionality. They tend to be linear with very weakly nonlinear properties simply because they're so thin, so small structures that the inherently weak nonlinear effects in optics do not allow us to see strong nonlinearities. And they are inherently limited by symmetry. If I build a single surface that interacts with light, then I have geometrical symmetries that come into play and limit my efficiency, but also time reversal symmetry that, of course, limits what we can do with these surfaces. And that's where our work in the last couple of years has been focused on, in trying to overcome these limits and propose metamaterials and plasmonic structures that can overcome these properties, looking at hybrid surfaces that are surfaces that combines different phenomena on the same platform. So not only electromagnetic resonances, but also other type of resonances that can be optomechanical, can be quantum, like material resonances, in general multiphysics responses, and active or time modulated or even mechanically moving structures that can overcome some of these limitations. So in this context, one of the things we have been doing, this work is in collaboration with Misha Belkin from my department at UT. has been to look at the combination of these metasurface concepts with material substrate that provides very large nonlinear responses. These are multi-quantum well structures in which we can actually engineer at will these intersubband transitions to enhance nonlinear responses at specific frequencies. And as this is a well-established material platform that provides large nonlinearities for electric fields polarized along the orthogonal to the layers. And the idea was to use this as a thin substrate to boost the effects of metasurfaces printed on top. So we use plasmonic structures printed on top of this thin multi-quantum well layer, and we look for ways to enhance the effective nonlinear response of these surfaces. And we have proven, for instance, in this paper that indeed one can get effective surface susceptibility, nonlinear susceptibilities that are much stronger than what you would expect from such a thin layer. So you can get reasonable efficiencies of nonlinear operations, in this case the second harmonic generation, over structures that are very, very thin. The idea is that these structures, that the unit cells, the pixels that combine these metasurfaces, have to provide at the same time good conversion between transverse fields that hit the surface and vertical fields that engage these nonlinearities, and also large field enhancements and conversion from one frequency to another if you want to do mixing. The goal is really to enhance this overlap integral here at the pixel level. This is mid-infrared. This is done at mid-infrared frequencies. So in this specific example is second harmonic generation from 8 to 4 micron wavelength. I mean hundreds of nanometers. The thickness is 400 nanometers, and the pixel size is in the same scale. So it's smaller than the wavelength. It's actually 20 times smaller than the wavelength. So that's exactly the whole point of what we're trying to do. We're trying to show that you can get reasonably large nonlinear effects over scales that are very subwavelength. You don't need to worry about phase matching at this scale of the wavelength, but you can produce enough nonlinear response in these subwavelength pixels. These are some of the latest results in which we optimize these structures to be etched so that the fields are confined under these plasmonic structures, and they overlap quite well as the resonant modes at the two frequencies, at the fundamental and second harmonic, and you can get quite reasonable conversion efficiencies with very low input powers and get out something that you can measure at the second harmonic frequencies. The vision we are looking at is to think of a surface now in which you can control each pixel independently and get some nonlinear operation out of this structure, and not have to worry about volumetric effects that work only after like a large volume, but in this deeply subwavelength pixel you can get enough nonlinear conversion out. In this direction, we've looked at this specific structure in which the unit cell is designed to maximize the nonlinear conversion, but then we are exciting the structure with circularly polarized light so that independent of the rotation of this structure, you get the same nonlinear conversion efficiency, but you can control the phase of the nonlinear generation, because rotating the structure geometrically implies essentially a retardation or advance in phase compared to the given excitation. If you do the math, you find that actually the nonlinear currents, polarization currents that you induce in the substrate have the same effective chi2 on the surface, but the phase of the nonlinear currents is controlled by the rotation phi, the geometrical rotation of each pixel. So effectively you can pattern the surface as I showed you for the linear case before, but now for nonlinear operations. You can control the nonlinear phase, the phase of the nonlinearly generated beam by controlling the rotation of the structures. If you excite the same structure with opposite circular polarization, the signs of these phases flip, and that implies essentially opposite phase profile on the surface that is controlled by the external excitation. This is an example. We have worked on different samples, but this is a case in which we are controlling the rotation by applying a linear gradient of the rotation angle. And this way, when you excite the structure in normal incidence, the nonlinear generated beam is steered towards a certain direction that depends on the gradient of the rotation of these pixels. And you see that the beam that emerges out at the second harmonic is actually steered, even if we are always exciting in normal incidence. Of course, if you change the pattern, for instance, you choose a parabolic rotation, you get focusing or defocusing of the generated beam. So this one is one possibility to boost nonlinear effects on metasurfaces, on very thin structures, but another direction we've been pursuing is trying to see how to break those symmetries that I described before. If I have a single surface that is interacting with light, then it's easy to see that, first of all, when I excite from one direction, if I couple to this direction, I have to couple the same amount with same efficiency in the other direction because of geometrical symmetries. And temporal symmetries tell me that if I invert the time, so I send a beam from this direction, I have to couple the same amount in the opposite direction. This is time reversal symmetry. It doesn't have to be. But here I'm simply assuming that the structure has some spatial inhomogeneity. As long as it's only spatial inhomogeneity, that has to obey geometrical symmetries in the transverse plane, because I have only one surface, and temporal symmetries, because it's a static structure that is time reversal symmetric. So we're trying to fight these limits on what I can do with a single surface. What boils down to, I want to fight reciprocity. Right? Reciprocity in general implies that if I send a signal from point A to B, when I invert it and send it from B to A, I get the same transmission coefficient. And this is a well-known principle. That's why when I talk to you, typically you can talk back to me or send a signal back. But there are many situations in which we would like to get isolation to protect the source or to avoid interference from echoes, or circulation. This is a circulator is a three-port device that essentially combines three isolators in one. It allows me to send a signal from port 1 to 2, but when the signal comes back from 2, actually goes to 3, and from 3 to 1. This non-reciprocal circulation is very useful. Today, actually, it's a very hot field because of the possibility of realizing full duplex, of being able to transmit and receive through the same antenna at the same frequency at the same time. So you can essentially use better the spectrum. Today, in cell phones, we transmit at one frequency but receive at another one because we don't have circulators on a cell phone. The way we build these devices today is using magnetic bias. And the reason for that boils down to how Lorentz reciprocity theorem is derived from Maxwell's equations. This comes straight from Maxwell's equations, provided simply three assumptions. One is that your materials are symmetric, are time reversal symmetric, so the tensors are equal to their transpose. They are time invariant, and they are linear. These three assumptions and Maxwell's equations give you this general symmetry result. So the way we break today reciprocity and build isolators and circulators is to break the first of these assumptions. That is, we bias our materials with a DC bias that makes the materials asymmetric. Now, they are not anymore time reversal symmetric. If the wave travels along the magnetic bias or against it, it fills two different materials. And with the smart engineering, you can indeed build circulators or isolators. The problem is that magneto-optic effects are typically very weak. They happen in materials that are not that available, like ferrites or ferromagnetic devices, and that are difficult to integrate on CMOS or silicon. So it doesn't exist today a circulator that you can just plug into your cell phone. You would need a big outside bulky device to do that, and that's not practical. That's why we have been starting to look a couple of years ago in my group in breaking reciprocity using these other two approaches. I will show you a little bit of our progress in this area. The area of time invariant materials actually has been pioneered by Chanhui Fan and Etan Wang that a few years ago have shown that if you have, for instance, a waveguide in which you start modulating the index, you can actually realize an effective non-reciprocal response because the waves that travel along the modulation direction or against it fill different waveguides, and you can realize different conversions. They did it in optics and in RF. These devices still are quite bulky. They require many, many wavelengths because, again, modulation effects are not that strong on the mode itself, and they're kind of perturbation. So what we've been studying is ways to make these devices practical and exploit a different way of using time modulation or even mechanical motion to break reciprocity. I will show you how we came with the idea. The idea was inspired by really looking at how magnetic materials work. If I apply magnetic bias to a ferromagnetic material, what I do is actually split the degeneracy of these states, the left-handed and right-handed state. And this is called the Siemens Splitting. It's linearly proportional to the amount of magnetic bias that you apply to the material. And that's how actually magnetic circulators work. This splitting tends to be require quite large magnetic bias, and that's why you get these devices. What we looked at is can we replace the magnetic bias with something else? And the thing we relied on is angular momentum rather than magnetic bias. So we took a circularly symmetric cavity, empty, and we started looking at what happens when we spin air or whatever medium is in the cavity. It happens something very similar actually. So if the medium is still, then the fundamental modes of this cavity are degenerate. Left-handed and right-handed resonate at the same frequency. But when you start spinning the medium, then again you open up, you break this degeneracy. One mode resonates at lower frequencies, one mode at the higher frequency. You can explain it easily with Doppler shift, basically. The mode that goes against or with the medium feel different lengths of the cavity. This is easy to do, for instance, in an acoustic scenario, and that's our first experiment in this area. We took a hollow acoustic cavity. We first excited it without moving anything, and when you excite it at resonance, of course, the wave splits between the two channels. It's symmetric. But then we started spinning air in this cavity, and you notice that now the mode from port 1 goes to port 2, and port 3 is actually isolated. You notice also interestingly that the standing wave you excite in the cavity is actually asymmetrically excited because of the spin, and it aligns at 0 exactly on this port. So there is a specific velocity that makes it work. When you excite the wave from port 2, actually it flows to 3. So now you see it's non-reciprocal. This is like what a circulator is. And from port 3, it goes to port 1. So the circulation of power comes from the motion of the fluid inside. But what's surprising is that the velocity required to make this work is much smaller than velocity of sound. It's not that you need to spin air very, very fast. This is actually 500 times smaller than velocity of sound. And yet you get full isolation in this compact device. This is actually less than a wavelength large. So this was the first circulator for acoustic waves. I mean, it's a very simple experiment, actually. It's audible frequencies. It's a 3 CPU fans. That's because we don't need that much speed. And we can control with applied DC voltage the speed, so we can tune it to the right velocity, and then you can actually hear that sound from port 1 goes to 2, but from 2 goes to 3. This is an experiment you can do just listening to the in fact, you can tune the velocity just with your own ear. Now, we are in the business of metamaterials, so the next thing we thought about is, can we use this as our meta molecule, our building block to build actually a material or a surface out of this? Because our goal at the end was really to build these surfaces that don't obey time reversal symmetry. So we looked at this simple hexagonal structure of circulators, acoustic circulators. Each of them has their own motion of fluid in it that is moderate but still breaks reciprocity. And for now, let's assume that these are actually ideal circulators. So they isolate quite strongly. By the way, the isolation we measured in that system was 40 dB. So it was significant. It's 10,000 times contrast between the two. Even if it was like an in-house setup, it's nothing fancy. So if you excite the structure in the bulk of this system, this is what happens, right? You go from this node to this node to this node, and the wave is trapped, cannot get out of this node. Essentially, this lattice does not support propagation in the bulk. But if you excite it on the edge of the structure, then you notice that from this node, the wave goes here. When it hits an edge, it cannot come back because it's a circulator. It will actually go this way and then come back here and keep going on this edge. Whatever you do to this edge, you, for instance, eliminate this point here, the wave has to find its route again on the edge but cannot go back. This is exactly what happens in topological insulators for electrons, but now we are doing it for phonons, for particles essentially without charge, right? That this lattice can support propagation on the edge, that is one way, does not support propagation on the back of the back mode, whatever happens to the edge, but does not support propagation in the back. And it's very robust. In fact, it's topologically robust because the topology of the band diagram ensures you that this mode throughout the band gap exists. These are full wave simulations for this mechanically moving structure for a strip. So it's a 1D structure, and we're looking at the modes. You notice there are two modes in the band gap that are edge modes. One is this mode that goes this way, and this one is the other mode that goes the other way. Of course, this is the same mode that is closing at infinity. It's just one-way propagation. So this confirms that you can get that. And these are simulations of finite structures in which you see indeed edge modes that do not back reflect, are always going in this direction, and reconfigurable waveguides that travel along the domain wall between two opposite spins of this mechanical bias of the two molecules. So you can reconfigure this by simply changing the spins, and you will get this one-way broadband propagation along this domain wall. Now, can we push this into optics or into RF? Of course, if you want to do that, you still have to mechanically move media much faster than you do for sound. So that's why we went into this idea of actually building, and again, an azimutally symmetric cavity, but instead of mechanically moving the medium of the cavity, we are actually temporally modulating it. As I said at the beginning, it's time-varying structures. In this case, we are modulating the index to look like an azimuthal, an angular momentum bias, even if there is nothing that really mechanically moves. Also, in this case, you can prove that you have this Siemens splitting for the modes of the cavity, and you can exploit it to realize ideal isolation for these structures. What's nice is that, again, the requirements on the modulation amplitude and frequency are very relaxed. Here, for a Q factor of 7,000 for this micro-ring silicon photonic resonator, you need a modulation amplitude of 10 to the minus 4, and also a modulation frequency in the order of few gigahertz. This happens at 1.5 micron wavelength. So there is a huge contrast between modulation frequency and signal frequency, yet you can get large isolation in a system that does not require anything that is not already in a silicon photonic circuit, in a nanophotonic structure. These are 3 PIN junctions that are modulating the index of this micro-ring resonator, and yet they produce full transmission in this direction and isolation when you go in the other direction. We built this system at RF. This is a circuit that builds this effect. It's LC lumped elements. The capacitors are actually variable capacitors that can be tuned by an applied voltage. So we apply modulation signal with different phases, 0 degrees, 120 degrees, 240 degrees. So the circuit looks like it's spinning very slowly as the input wave comes in and out, and that allows you again to realize large contrast between the propagation from port 1 to 2 and from 2 to 1 and isolation. In this system, we measured up to 80 dB isolation. Actually, in this, we are now at generation 4 of these elements. This was the first demonstration in this paper, but since then we have done a lot more improvements, mostly in terms of linearity of performance, because of course, by the way, this system is completely linear. This is a parametric effect, so it doesn't matter what's the input signal intensity as long as it's not going to, I mean, basically the nonlinearity comes from the varactors itself. So the components we're using to modulate happen to be nonlinear, and there are tricks to cancel out the dominant nonlinear responses, so you get a very clean linear response and minimal insertion losses. Again, also for this system, you can build the equivalent of a topological insulator for RF, for electromagnetic waves, or for optics. So in this case, these are all resonators that are excited or modulated with different phases. All have the same modulation frequency that is much smaller than the signal frequency, but the phase of each element is patterned in such a way that you open this topologically protected band gap with one-way edge mode for radio frequencies. And they are indeed non-reciprocal. They travel along the edge without reflections. They cannot couple to backwards mode. And they are very robust. This example is the simulation for an ideal modulation phase pattern with the edge mode. And this is what happens if you add a random noise to the phase pattern of these elements, and you see again how the edge mode is preserved because it's a topological order, right? It's you cannot break it with continuous changes in the response of the system. One thing I like of this is that I showed you at the beginning that response assuming an ideal isolation and circulation, that was one frequency, right? But now in this plot in which I show again a reconfigurable waveguide at domain walls between two domain walls, in a domain wall between two domains, I plot the isolation levels and transmission for the system, and then I plot also the transmission coefficient for the single element forming this lattice. What I find impressive is that, of course, here the isolation happens only at one frequency, but in the lattice you open a continuous band gap over which there is this full isolation, even at frequencies for which each of the elements is almost completely reciprocal, right? The transmission from both sides is almost the same. But yet when you put it in a lattice, because of this lattice resonance, essentially, this band gap, you get this nice isolation over continuous bandwidth. We were looking at bringing this concept from guided waves to open free space radiation, and this has two important implications. One is in terms of photovoltaics, and one is for antenna systems. If you look at what reciprocity implies for these systems, you understand easily from Kirchhoff's law that if a system is designed to absorb well from a certain direction, has also to emit well towards that direction. At the same time, if an antenna can transmit well in a certain direction, has also to receive well. Typically, in antennas, we don't even bother in measuring both transmission patterns and reception patterns because first chapter of any antenna book tells you that they are the same because of reciprocity. Well, what we've been looking at is building systems that can absorb without emitting or can transmit without receiving, based on this principle of time-varying systems. The idea we used was to start from a conventional antenna platform. It's called the Leaky wave antenna, if you're familiar with the radio frequency systems. Essentially, it's a periodic structure in which the band diagram folds to go inside the light cone, so you have good radiation towards a certain direction for a certain frequency. But this, of course, is reciprocal in a conventional Leaky wave antenna. But then we imparted the modulation that works like a traveling wave this time. So now if the signal goes parallel to the traveling wave, fills an antenna. If it goes against the traveling wave, modulation wave, it fills a different antenna. And you can design it in a way that from one side you have good interband transitions from different sides, but from the other side you get very weak transitions, and therefore you get very different contrast between the two. This was the experiment. It's actually very simple Leaky wave antenna. Friends in antenna community would say that this is not really a good Leaky wave antenna because it's very short. It's actually only one wavelength long, but it's periodically modulated. And now in these periodic structures we put varactors, so that when we excite the structure from this port, and this port is impedance matched both for the modulation signal and the RF signal. So the modulation signal, it's a single tone that travels along the antenna, doesn't radiate, but it modulates these varactors with a traveling wave, like a Tapirulano, an airport. Right? It's the same, essentially the same physics. But then the RF signal that travels parallel to it gets radiated out very efficiently, but anything that comes back feels a different antenna because of this breaking of time reversal. And that leads to these measurements. In transmission, we get transmission reception, we get identical patterns for modulation frequency 0, but then we start in the input, we add this tone, this modulation tone, and we get very nice directive radiation, but no reception. This antenna transmits without receiving. So it shows that you can indeed build a non-reciprocal antenna with large isolation, actually, based on a simple structure. At the end, we don't need to modulate each element. We are just sending the modulation signal from the same port where we send the RF signal. Now, I told you about these time-varying structures and mechanically moving structures, but another direction we've been quite excited to work on has been the area of nonlinearity. This is interesting because we can think of now having systems that don't require a bias and yet break reciprocity. Right? We went from magnetic bias to other forms of bias. I showed you angular momentum bias or linear momentum bias in these examples, but still there is some bias you need to apply. And now we would like to see if nonlinearities can self-bias the material and get us away with no reciprocity. This is actually a topic that has been, again, quite explored in recent years. These are few papers that show nonlinear isolators based on this principle. Actually, if you look at all these papers, while they show some form of isolation, the insertion loss is typically huge. And I will show in a moment why this happens and how we can get around this challenge. But first, let me explain you how they work, these systems. So imagine that you have a resonator. A resonator at a certain frequency has, for instance, a dip in transmission. But now assume that this system is filled with a nonlinear material, like Chi3, some nonlinearity that depends on the local intensity of the field. Now, if I pump more intensity, what happens is that the resonance frequency shifts, and shift with this law, right? The frequency shift depends on the overlap integral of the change in index due to the nonlinearity times the modal distribution of the field. That implies that if I can build a structure that when excited from the other side has a different type of field distribution, that gives me a different distribution of delta epsilon, a different modal integral, and that can lead to a different frequency shift. So exciting from opposite directions, now the structure looks different because the field distribution that I induce is different, and then I can get a system that indeed is a nonlinear isolator. This does not require an external bias, it still breaks reciprocity. The key is to get as large as possible of this number kappa, that is the asymmetry factor. How much I can induce a certain field here that is different when I excite from the left and from the right. Right. Now, what I will show you is that, interestingly, that number is fundamentally bound by time reversal symmetry. And that explains why all the nonlinear isolators that have been built and published so far all work quite poorly. So the way to show this is quite simple. Imagine you have an arbitrary structure. This is a very general proof, actually, that when excited from the two sides has the same transmission because of reciprocity. I'm assuming that the system is linear for the moment. And I'm also assuming that it's lossless, even if the lossless condition is just for simplicity. You can lift it and still the theorem applies. So it has the same reflection amplitude and the arbitrary phases. But then I apply time reversal operation to the second structure, and that implies that if I excite the structure with these two waves, I get out the unitary wave, and I get the conjugate of the field. Right. Now I can use here time superposition principle, and I get this formula. At each point in this volume, whatever this volume is, this can contain as many modes as you want. At any point, this has to apply because of time reversal symmetry. The field induced from the left conjugate is equal to reflection coefficient times the field from the left plus transmission coefficient plus the field from the right. It's just this. Now, then you can apply this inequality, and you get this quite interesting formula. This tells you that at any point in your structure, the ratio of fields that you induce when you excite from the left and the right is bounded by the reflection coefficient at the ports. Or in other words, the transmission coefficient fundamentally is limited by the asymmetry factor. If I want a very large asymmetry factor, that will give me a very low transmission coefficient. That's why those nonlinear isolators actually were very good at creating asymmetries, but they were very poor at transmitting. So insertion loss was huge in those systems. This might seem counterintuitive, at least it was to me when we derived this, so we tried it. I mean, let's see if it works. Let's take an asymmetric cavity, 2D cavity. You excite it from the two sides, very different field distributions as expected, but then let's match it. So let's add a matching layer here. Now it's matched, it transmits everything, but you notice that the field distribution is identical. Despite the cavity being very asymmetric geometrically, if you want to transmit, you need to have the same fields everywhere. And this applies whatever your cavity is, as asymmetric as you want it for geometrically. So basically the bottom line is that you want asymmetry, you pay the price with the insertion loss. This is just a proof that any frequency you pick, you are always inside these bounds that we derived for the field symmetry. Now, it still misses a piece to complete my proof, because now I'm dealing with linear systems. How does this apply to nonlinear systems? Actually, you can apply to nonlinear systems if you assume that your nonlinearity is concentrated in one resonant mode, as all the isolators presented in the literature so far. If your nonlinear isolator is formed by an arbitrary number of modes, but only one of them is nonlinear, and is described by this law, like frequency shift is proportional to the intensity applied, then you can describe the amplitude of this nonlinear resonance as a function of the linear response through this expression here, and then you can actually relate the frequency shift of the nonlinear case to the linear case. And what this formula tells you, it's quite interesting, is that the response of this completely arbitrary structure, the only assumption is that the nonlinearity is focused in one mode. It's identical if you scale the excitation from the two sides by the linear asymmetry coefficient kappa. That's why this is extremely important. The linear asymmetry coefficient is what governs the nonlinear response. So what I'm saying is that if I take an arbitrary structure like the one I showed you, the response for changing intensity is the same, just scaled. And the scaling factor is the asymmetry coefficient in the linear case. But this implies, as I showed you before, that if the asymmetry coefficient is 1, these curves overlap and the transmission coefficient can become unitary. If I want this to be large, that's what I want to get an isolator, then I have to sacrifice transmission. So the larger I want my asymmetry, the more insertion loss I will get for my nonlinear isolator. Actually, you can build maps to control this. You can build optimal nonlinear isolators based on a single nonlinear resonance. And these are examples. For instance, the only difference between these plots is this coefficient x. The x is essentially the Q factor. Basically, what I'm saying is, if I have a sharper Q factor, I can get a response with a smaller asymmetry factor, because I can get these closer together and still see the difference because the bandwidth is so narrow, and then I can get a better transmission. If my quality factor is low, I have to get larger asymmetries, and therefore my transmission is lower. So for a given bandwidth, you can get optimal isolators that are something like this, full isolation on one side, but never perfect transmission for any bandwidth you have. These are 2 points that give you the same transmission, actually. These are optimal points. And you can actually build one of them. We've been working again with Misha Belkin to try to build one of these nonlinear isolators based on multi-quantum well structures with mid-infrared excitation. And indeed, this is the type of response you expect, but it's not optimal. What's interesting is that we recently found that you can get away with this. I showed you that this theorem holds in the general case of a single nonlinear resonator, but if you actually study the case in which you have more than one nonlinear resonator, actually that theorem holds only to some extent. You can basically the trick is that you can get bistable responses in which one of the responses is not symmetric, and therefore you can actually get a nonlinear isolator that is fully transmissive from one side, fully reflecting from the opposite side. Basically, the trick in a simple system of two nonlinear resonators is that when you excite them from one side, both of them transmit for the same intensity, but one has a zero in transmission for lower intensity, so it blocks transmission from one side and not from the other. And that's actually the realization of this. These are only simulations for now, in which we have two nonlinear metasurfaces with asymmetric responses each. One has this resonant response, one has this Fano response in terms of intensity, designed indeed to follow the rule I just gave you, and this is the response you get. Notice that these are the two branches when you excite from left and from right. Notice both branches have a solution for which they fully transmit at the same intensity. This is actually what our theorem before actually requires. You always have this double solution here. But you can have another solution because of two nonlinear resonators that actually isolate. And you can make this hysteresis very large. So for a broad range of input powers, you actually get isolation from one side and full transmission from the other one. So this, you see a temporal excitation of the structure. This blue signal is the input signal. The red one is the signal when you send it from one side, is fully transmitted, and from the other side is fully reflected. So now you can get an ideal nonlinear isolator based on two nonlinear resonances, based on this bistability. This actually, we built it. This is a circuit based on two back-to-back varactors that design this nonlinear response. We can tailor it, and this is actually the measurement. So indeed, we got actually pretty broad band response over which we get nice isolation from one side and full transmission from the other side. Now, here the loss of the components that we used limit the transmission, but there is no limit in principle. And this is actually a larger transmission than what you would get from the optimal nonlinear isolators based on a single resonance. So we beat that limit, as I showed you before. I talked about topological insulators, and then we looked at, can we use these elements again to build self-induced topological insulators without an external bias, but yet they can create topological states as a function of input intensity. You can do that. So far we have shown it for a 1D array. So it's a chain, it's an array of resonators in which the nonlinear coefficients are actually nonlinear. If you study this structure, it has a band gap, and what's interesting is that this band gap evolves as a function of intensity. It's topologically trivial for low intensities, it closes at a certain threshold intensity, and when it reopens, is actually topologically non-trivial. It supports edge modes. As a function of intensity, there's no bias here, yet you can trigger this topological transition in a band gap that supports edge mode. You can see this more specifically if you look at the eigenmodes of a finite system, like this is a 40-element array. We look at the eigenmodes closer to the band gap. They are out of the band gap, but they actually enter the band gap as the intensity grows and become edge modes inside the band gap. The distribution of the fields from low intensities, these are bulk modes outside the band, in the band propagation regime, and then as the intensity grows, become edge modes that are sustained at the edge of the structure. And indeed, you can prove that the topological number of these modes is actually this band gap transitions from 0 to 1. You can see this also in these temporal simulations. So here we are exciting from the edge. In low intensity, you get these bouncing, propagating modes. You see clearly the Fourier transform has a band gap, as expected, and the winding number, this topological number for the chain, is 0 throughout the chain. But if you increase the intensity, you get to a point in which actually you get a nice edge mode. And clearly inside the band gap, clearly decaying in the array, interestingly, doesn't decay to 0 as in conventional linear topological insulators, because if it would decay to 0, it would actually transition to a different topological order. So you can prove that these modes analytically decay to a plateau that is exactly the threshold intensity that closes the band gap. As the band gap is closed, these are flat modes that travel flat throughout the array. And the topological order is indeed 1 throughout the array. We built also this system. This is again a circuit. These are 40 elements of these varactors that create this nonlinear coupling coefficient. And then we studied it in a low intensity regime. This looks like any circuit. At the input port, you see all these resonances. The dashed lines you see here are different measured input impedance when you actually change the array by breaking some of these elements. Right? We are removing some of these resonators here, and you see that the resonance of the structure actually changes. But if you excite the same structure with the high intensity pulse, you see that the input impedance is completely unaffected by the defects in the bulk, despite the fact that the modes actually propagate through the bulk at the intensity threshold. And that's because of the topological robustness. The response is very clean. There is a clear edge mode. We have been actually quite interested recently in looking at also how to bring this concept to statics. So far I showed you dynamic systems that has been studied quite extensively in the last few years. In this case we are trying to look, to break again its principle of microscopic reversibility, but in statics. So what it means is that we are looking at another theorem. It's called the Maxwell-Betti theorem, that implies that if I apply a static force to a certain object, the object moves on the other side by has a certain displacement. When I apply the same force on the other side, I expect to have the same displacement. That's what typically happens in static systems. We have been looking at systems that, again, combining asymmetry and nonlinearity can break this symmetry of response for static forces. And indeed, we were able to show in these fishbone structures that have these strongly nonlinear properties, this 20 dB isolation for static applied fields. So I push from one side and I get some displacement. When I push it from the other side, I get 100 times less, basically. And these are actually 2D structures that realize this effect and boost it, actually. This happens also for very low input forces, much smaller than for the fishbone, because they rely on this topological mechanics, in this case, these different winding numbers when you excite from opposite directions. The last few minutes of my talk, I wanted to talk to you about cloaking. That was one of the promises of the beginning of my talk about what can you do with these structures. We've been working in this area for a long time. Our first paper together with Professor Engeta in this area was from over 10 years ago. I was a graduate student at the time. And what we showed in that original paper was that if you want to suppress the visibility of an object, that is, to suppress the scattering of an object, you want to design a coat that actually cancels scattering at all angles, right? So you can design a metamaterial coating that scatters light with opposite phase, such that at all angles it cancels scattering, and the final result is that you have full transmission, full transparency from this object, because there is no scattering. Notice this is very different than stealth, right? There is no absorption here. We don't want to absorb light because we would create a strong shadow. That's scattering. We want to actually redirect all the scattering so that it becomes actually fully transmissive structure, transparent structure. Over the years, we have looked at these also implications for sensors, to build invisible sensors that can receive energy without scattering, without perturbing the environment, even in the near fields. These are some of the most recent experiments we have done in this area with these metasurfaces that surround actually dipole antennas. You can build antennas that are very low scattering. They have much reduced radar cross sections over all angles, even in the near field, but at the same time are very efficient antennas, both in transmission and reception. And also over quite interesting bandwidths, like this is LTE band for wireless communication. However, we also showed recently, this is just came out, this paper with Francesco, my student, we derived some fundamental bounds on how much of a bandwidth you can achieve with these clocks. And actually, the news are not so good. What we showed is that actually, if you want to get ideal cloaking with zero scattering, this can happen only over a zero measure bandwidth, only over one frequency. That's just causality that requires that. Also, we found some quantitative bounds for how much bandwidth you can achieve for a given level of scattering reduction. And this bound depends only on the size of the object you want to cloak. The larger is the size, the more this bound becomes restrictive, becomes like a knee structure. All possible cloaking approaches, including the one I just showed you that we work on, but many others like transformation optics, clocks all have to fall within this bound because they're derived simply by passivity, linearity, and causality. And that's why we've been quite interested in looking at active clocks that actually are expected to lie in this area and see if we can pump energy into the system and break some of these assumptions. And we realized that this idea of active cloaks is actually quite exciting, especially if you combine it with another interesting field of science, that is the field of parity-time symmetry. Parity-time symmetry is started in quantum mechanics, and it's a field of physics that is interested in these Hamiltonians that are not Hermitian, but yet they support real eigenvalues. In optics, they correspond to systems that have balanced the gain and loss in the same structure. So when you invert space and time, you get the same structure. That's why it's called the parity-time symmetry. It turns out that if you do the math for a geometrically symmetric object like a cylinder or a sphere, and you look at what is the recipe of the surface required to surround this object to make it ideally invisible at one frequency. If you do the math, you get this. This expression, interestingly, is parity-time symmetric. It's a system that when you revert it in space and time, you get the same system. And it's a system that works quite easily, actually, physically. On one side, it's an ideal absorber. It's like a stealth surface. On the back side is the time-reversed image of that. It's actually a laser. The combination of these two, they talk through scattering. They're not connected, right? They're just talking through the scattering here and there. Allows you to get a fully cloaked cylinder. And this is independent of the size of the object. Of course, it requires active systems. The passive side is a stealth surface. The active side suppresses shadows on the back and creates a full response that is cloaked. You can actually build these systems fully stable. That was our main worry. We're dealing with active systems. Are they stable? Actually, that's how the systems respond in time. You notice that after some transient, the system actually manages to reach steady state in which the object is fully cloaked. And of course, you have to make sure that the poles lie all in the lower complex of plane. And this is achieved by engineering actually the frequency dispersion of these components, of these active components, to make sure that the stability is ensured for any excitation, even when excited from the active side. To realize this system, we have been working on this now for a while, but the first step we took was to try to realize a 1D version of this. That is a system with, actually in acoustics, it's two loudspeakers loaded with a passive element and an active element, back to back. They are, again, one the time reversed image of the other in terms of impedance. So when you excite it from one side, this system is fully transparent, even if this object is actually passive, it's actually absorbing the energy. But this object is active, and it has the job of emitting an exact replica of the impinging signal that will essentially reach after the transient in which it torques to the passive system and they find an equilibrium, they get the signal. This works for any signal coming in, but also for any distance between the two. After a steady state, they will find the right balance after the transient to get this full transmission. From the other side, the system is reciprocal, so it still transmits fully the signal, but it has also strong reflections because there is an active speaker on one side. This was the experiment for this 1D system. The two loudspeakers loaded with circuits. The circuits are not connected. They're completely apart. They talk through waves in the transient. And this is the experimental results. You see full transmission, zero reflection, and what's more important, the absorption is actually twice the input signal. So the absorption not only, basically this is an absorber that does not create any shadow. So not only it absorbs very well, it absorbs actually twice as much power as you send in. And the reason for that is that the active signal is sending, the active speaker is sending back to the passive one an exact replica of whatever it's getting from the other side. This works in steady state after they synchronize automatically. You don't need to actually control anything here. I told you that this works for arbitrary distances, right? So what's interesting is that for the active side to be able to transmit a replica of the signal back to the passive side with the right phase, it has to actually emit the signal that is phase advanced. And therefore, the larger you make this distance, the more, this is a Smith chart, it's a complex plane transmission coefficient, it advances in phase. That's exactly what you need to realize negative refraction. What I showed you at the beginning about one of the holy grails of metamaterials, now I'm suggesting that you don't need a metamaterial to create negative refraction. you can get this phase advance through a material by combining loss and gain at the two edges. The material in between is just air here, yet you expect a negative phase coming back from the active side. This actually is what happens if you put an array of these passive elements in front of an array of active elements. However distance you choose, you get this negative refraction of the beam. And this does not come from a wave traveling backward with a positive power flow. This is actually a negative power flow going from the active side to the passive side in steady state in air. And you can realize a lens. In fact, these are some recent, this is coming out now in Physical Review X, in which we showed that indeed you can create a lens based on this system, just passive surface and an active surface in front of each other, for which you get ideal focusing without aberrations, because this point and this point are both focus of this strange lens in 3 dimensions actually. This even beats the idea of a negative index lens, because negative index lens typically works on a plane. The focus is actually very much aberrated in the 3rd dimension. This works in all 3 dimensions. Anyway, this concludes my talk. I showed you that the field of metamaterials, metasurfaces, is quite rich, especially if you enrich it with concepts like hybrid materials, with mechanically moving parts, time modulation, large nonlinearities, asymmetries, and gain. All these components make challenge actually a lot of the current technology limitations, and actually enable devices from radio frequencies to acoustics to optics that are quite interesting in terms of the physics and the engineering of these structures. Thanks very much. Yeah, that's a good question. Also, all depends on what frequency you're talking about. I'm guessing you're talking about optics. So, yeah. Shrinking. Yeah, that's a great question. First of all, some of the stuff we're showing here is mid-IR for the reason that we're engaging these inter-subband transitions. We're looking into, together with Misha Belkin, into working with interband transitions in semiconductors to push it higher in frequency, and that's one idea. We would like to do DFG also, like to create terahertz radiation out of this. But the challenge again is to combine these very small resonators in these structures, and at some point you end up with these challenges in fabrication, losses, and also one of the big challenges we're fighting these days is saturation of these structures. Like at some point, we show these very large nonlinearities with surprisingly low intensities, but as the intensity grows, these materials saturate their nonlinear response, because typically we engage hot spots. The fields are not really distributed as nicely as we would like. They are mostly focused near the plasmonic structures, and that limits. So we have a PRB paper in which we discuss these challenges, and we predict that if we were able to build the right materials and the right structures, we could push to efficiencies up to 10% for in these very, very subwavelength structures. But so far we've seen much lower efficiencies because of the saturation challenges. So there are several things we're looking at, but we are excited because the good thing is that we're illuminating it with the power of a laser pointer, basically, and we see stuff coming out at second harmonic. It is already surprising. But of course, there is a lot of work to build it into a device that really makes a difference. Yeah, that's a good. I'm assuming you are talking about these multiplexing systems with using orbital angular momentum. So that's interesting. There has been a lot of work in the area of metamaterials using these. In fact, Bob Nevels has been interested in this. So in the area of RF communications, there has been a lot of work in the area of MIMO, multiple inputs, multiple outputs, and there are probably even better ways to get multiplexing into practical antenna devices, not necessarily using orbital angular momentum. I've not worked myself in this area, but I'm skeptical about the fact that this circular polarization on its own is fundamentally different than using conventional MIMO techniques, and there are many exciting works in the area of massive MIMO, for instance, today. This huge throughput using multiple antennas to control probably in a more efficient way than with circular polarization the transmission. Yes. It actually learns it in the transient. It has to learn it in the transient. So it doesn't know on its own. But in the transient state, because the steady state, this is actually a natural mode of the system, it will evolve into that system. And luckily, we built it to be completely stable. So we don't risk to go into instabilities. But over time, I mean, we're assuming that the signal does not change frequency and phase throughout the transient. If it does change too fast, then the system wouldn't work because it doesn't catch up fast enough. But pulses, sure, yeah. So with short, if the pulse is shorter than the kind of steady state, in our best designs so far, we got around 10 cycles before we reach steady state. And this is actually quite interesting. It connects with what I was talking to you about these bounds on bandwidth, right? So for passive systems, those bounds are very stringent. These active clocks that we recently have been studying and we're trying to build, also in 3 dimensions, have much more relaxed bounds. But still they have bounds that don't come from passivity, but come from stability. I mean, if I run a simulation of these systems, I can assume these active systems to be very flat, non-dispersive. Then I get huge bandwidths. But the problem is that when I really build the device, it will reach instabilities very fast. So you need to tailor the dispersion to make sure that it's always stable whatever happens around it, and that limits the bandwidth. So the question we're trying to answer now is how broadband can this be keeping the stability in place? And it turns out that with a Q factor of 10, they seem to work quite well. That is pretty reasonable. And over time, the good thing is that it will never go into oscillations. The worst thing is that it will be visible for 10 cycles, and then it will adjust to the input. And it's all a problem of bandwidth. How broadband is your signal? If it's a pulse, very short, of course, no clock can work. I mean, this at some point is causality. I want the signal to go around the object the same speed as through the object, so there has to be some limitation of how short of a pulse I can transmit. Thank you.